Hello, welcome to Fundamentals of Acoustics. Today is the third day of the last week of this course. Since last 2 days we have been discussing some of the important points and techniques which we have to know when we are trying to conduct an octave band analysis. So, in these 2 days we have gotten sufficient information and knowledge, and today what we will learn is use this information to figure out how do we actually construct the plots which are required for performing octave band analysis. So, our goal is to learn how to plot octave band plots. Okay. So, we will construct one hypothetical plot. So, on the x axis I plot frequency, and on the y axis I plot either I have to plot decibels or I have to plot dBA. Okay. And what I do is I plot, first I select specific frequencies. So, let us say we are plotting the octave band plot, not 1/3 octave band plot. So, let us say I am starting from 125 hertz. So, this is my first central frequency, then this is 250, 500, 1000, 2000, and let us say 4K. I want to go up to 4K suppose. So, first thing is that I report these decibels only at these central frequencies. So, it will look like this. Okay. So, this is an octave band plot corresponding to octave bands with central frequencies 125, 250, 500, 1000, 2000 and 4000. Consider this point A. What does this point A mean? What this point A means is that if, so for the moment let us just consider that this is a plot on for decibels, not dBA. So, what does point A mean? What point A means is that if I have on this plot pressure, right. So, I can, our original data is what? In time domain. Using FFT or DFT, I can convert that data into frequency domain data. So, my frequency domain plot will be something like that. And on this plot, let us say this is 125 hertz. Let us say this frequency is what? 125 by square root of 2, and this is 125 times square root of 2. So, what this point A means is that all the energy associated with frequencies in this band, we somehow add them up and convert it into decibel units, and once I get decibels from all these frequencies, I put it at this single point. Okay. So, this single point gives us information about all the energy contained in this band, which has a central frequency 125 and which has a upper frequency 125 times square root 2, lower frequency of 125 divided by square root of 2. So, that is what it means. So, what this means is, so how do we compute all the energy? My FFT plot gives me this curve, it gives me this curve, But from this curve, how do I compute all the energy which is contained in this and somehow convert it into decibels? That is what our aim is. Okay. So, what do we do? So, the way I compute this decibels is through this step by step process. First, I convert PT into frequency domain. How do I do that? Using forward FFT, or which I have also called several times as DFT. Okay. Now, second, I plot the FFT curve against what? Frequency. How many plots will I get? Whenever I do an FFT, how many plots do I get? 2. I get one plot for magnitude. So, this is magnitude, and similarly I will get another plot for phase, and the phase will be from minus pi to pi. So, I am going to erase this line. So, let us say this is my phase plot, and so my phase plot looks something like this. So, this is upper limit is pi, lower limit is minus pi. Okay. And this is, let us say this is the band of frequency which I am interested in. So, what is this number? 125 divided by square root of 2, this is 125 times square root of 2, and this is central frequency Fc. So, this is my phase plot and this is my magnitude plot. So, we plot the FFT curve. Actually, it is not curve, it is curves. Why? Because there is a magnitude plot and there is a phase plot. So, we plot both of these curves. Then what is our goal? What is our goal? To add up all the energy in this band, right? So, add up all the energy in this band, convert it into decibels and plot point A. That is our goal. So, our goal is that we have to plot point A from magnitude plot and from phase plot. Okay. So, what do we do? We know so the third step is that make magnitude of all frequencies outside band of interest 0. So, we make all other frequencies. So, what I am going to do is this magnitude plot I am going to modify it. So, my modified magnitude plot will look like this. No, it will look like this. Now, if I erase it, so our original plot, one second, our original plot was something like this and our modified plot is purple. So, it is like this. What does this mean? Once I have made the amplitude of all other frequencies 0, what have I done effectively? I have eliminated the energy from all other frequencies except this band. Then what do I do? Then fourth, by the way, what happens to phase plot? I do not have to worry because I have made the energy 0. So, I do not have to worry too much about the phase plot. So, I do not bother with the phase plot. So, the next thing is, what do? I take the inverse transform, inverse FFT of modified plot. So, remember, when we are doing inverse FFT, we will have to use this information, magnitude as well as phase information to do the inverse. Why? You see it here, xk. Xk is not necessarily a real number, it has magnitude and phase, right, because it is a complex number. So, I have to use both these plots. So, I take the inverse FFT of the magnitude plot, and what do I get out of it? And get what do I get? If I take inverse of magnitude of modified plot and original phase plot, so in inverse transform, what do we get? Time domain data to get modified xn, and this is in time domain data. Okay. So, how will my time domain data look like? So, this is my time, and what will it look like? So, this is discrete plot. So, what will I get? I will get lots of points, right? I will get lots of points, and the y axis is PT and the x axis is time. Now, what do I do? This domain data, does it have energy associated with other frequencies except for this band? It does not, because we have made it 0. Okay. So, now what do? I calculate RMS of this PT, root mean square. How do I do? Let us say this is x1, x2, x3, and it goes on till xn. Actually, it will start with x0, x1, x2, and it goes on till x minus 1. So, to find RMS, what do? To find RMS, first I take the squares, S is a square. So, I do this root mean square, root mean square. So, I always go in this direction. So, first I take squares. So, P0 square plus P1 square plus P2 square Pn minus 1 square. Then what do? I take the mean. So, I take divided by n, and then I take the square root. I get PRMS. Then what do? Then now I calculate decibels. So, dB equals 20 log 10 PRMS divided by 20 into 10 to the power of minus 5. And in this way, I plot which point? Point A. Plot point A. Understood? Next thing I have to do is I have to plot point. Let us say this is point B. How do I plot point B? I do the same thing. In the other case, I make this new band and I make the magnitude of all other frequencies outside this band 0, take the inverse transform, get PRMS, and I plot dB for point B. So, likewise I get all these points across the spectrum. If I have to do 1/3 octave band plot, what do I do? Here I am plotting plots for octave band, there the band of interest at a given point of time will be 1/3 octave band. So, I find out sit lower frequency, higher frequency and consider only those frequencies in 1/3 octave band, make everything else 0 and so on and so forth. So, I hope this helps you understand how do we perform this octave band analysis. And in this case we have learned how do you construct a plot where on the y axis you have dB and on the x axis you have frequency. But we two types of plots. One is where on the y axis we plot dB and in the other case we plot dBA. So, now we will learn how do we make a dBA plot. So, goal is to make this plot. So, once again this is 125, 250, 500, 1K, 2K and so on and so forth, 4K. So, here our goal is dBA. What is the difference between dB and dBA? dB is based on pressure data as measured by the microphone, dBA is the pressure data as perceived by ear. So, what do we do is, so first step, we convert PT into frequency domain using forward FFT. So, we will get lots of points and it will almost look like a continuous curve, but let us say this is my dB curve, not dB curve. So, this is pressure as a function of frequency. Next, so this is frequency. So, here this is units is pascals, unit is Pascal, and let us say this is the magnitude plot and similarly we will get a phase plot. So, we do not worry about the phase plot, that does not change. The next thing is, so let us call this graph G1, let us call this graph G2. So, here we are getting G2. Now, we change from convert G2 to G3. What is G3? It is this plot. So, here I am plotting pressures in decibels. How do I convert this into decibels? Suppose this is some frequency F naught and here pressure is P1, then how do I convert for F naught? How do I calculate decibels? 20 log, is it P1? What is P1? Yeah, but what is it? Is it the RMS value? No, it is the magnitude. And these are specific frequency components. So, each frequency, what type of wave is it? It is a sinusoidal wave. So, the ratio between sinusoid for a ratio of RMS for a sinusoidal wave and its magnitude is square root of 2. So, I take P1. So, this is at dB at F naught and dB at F naught is what? At frequency F naught, which is this, is what? 20 log P1 by root 2 by P ref. Okay. So, this is important, otherwise our answers. So, likewise we construct a dB plot for all the frequencies. We construct dB plot for all the frequencies. So, this is our graph G2, G3. Next, what do we do? Convert G2 to G3. What is G3? G3 is a similar plot. So, this is G3 and this is G4. So, what is G4? On the x axis I am plotting frequency and on the y axis I am plotting dBA. So, this is the original, this is the dB curve, but now for each frequency I have to add or subtract the A weighting. So, this is dBA curve. How do I convert a dB curve into a dBA curve? For each frequency we have to calculate the weight. We have to calculate the weight, how much that point moves up or down by, and how do we calculate that? In yesterday's class we had calculated how do we calculate that weight AF, A as a function of frequency. So, I get this dBA curve. Fourth, convert G4 to G5. So, this is the perceived curve. So, what does this tell us? That for each frequency, what is the perceived decibel level? What is the perceived decibel level? And from that, we can construct P perceived. We can construct P perceived, and here the units are pascals. Okay. So, how do we do that? So, let us consider this frequency f naught, and let us say this is dB at f naught, actually it is dBA. At frequency f naught, then P perceived is equal to what? It is equal to 20 into 10 to the power of minus 5 times 10 to the power of what? This is dBA at f naught divided by 20, and this P perceived will be what? This will be RMS pressure, and what I want is into 1.414. So, I will get the peak pressure. So, this is perceived pressure at its peak value, understood? And then, so now what do we do? Now we start calculating energy or perceived energy in each band. So, suppose I have 125 hertz, then it has an upper frequency limit, it has a lower frequency limit. So, identify those limits. So, from this I am going to write follow method used to construct octave band plots on dB scale from here on. From here on. So, specifically what do I do? If I have to get the energy in this band, I identify this band, I modify this curve. so that all other frequencies are 0. Take the inverse transform of this modified magnitude curve, the phase plot remains unchanged, phase plot does not get changed, right. So, use the phase plot and this modified P perceived curve, compute the RMS, construct, get the value of dB, but it will not be dB, but it will be dBA, because it is based on this P perceived level, and develop the curve as shown here, as shown here. So, this is the overall approach. Okay. So, using this method we can do octave band analysis or 1/3 octave band analysis or 1/10 octave band analysis, whatever, but the overall approach is this kind of a thing. So, I hope this makes things pretty clear, because I think I have explained it in fair large amount of detail, and all this information, if especially if you are in an industry setting or you are a noise engineer, then this understanding of how to conduct octave band analysis will be very useful for your professional needs. So, with that we conclude the discussion for today, and we will meet once again tomorrow. Thank you.